Hello everybody. Today I want to talk about our efforts to develop and deploy automatic whale detection systems for real-time ship strike mitigation. And I want to start by acknowledging my co-authors, Sebastian, Loika, Alex, Dan, Bob, Fred, Mark, and Dave, who were tremendously helpful and played a big part in getting us out on the water and getting the systems to work. We all know that ship strikes are a big problem for the North Atlantic right whale, and current measures include mainly risk reduction methods like slowdowns and spatial temporal separations through management areas, which are on a large scale. We want to add another tool to the set of tools we have available, which is direct mitigation. That means it's vessel-based and would allow to change the ship, the speed or course if the whale is detected in its path. Ideally, such a system is informed by an automatic whale detection system, and of course this information could also feed back into the risk reduction large-scale management efforts. Our concept is very simple. We have a thermal imaging scanner that scans the ocean surface for whale blows, and if the whale surfaces, the system shall be able to detect and recognize the whale on the thermal signature. Now, we have used such whale detection systems for a while, and I have one example here for you. So here in the top you can see that right now there's nothing, and then the whale comes to the surface and the whale blow gets bigger and bigger and bigger. And of course you want to have a detection algorithm, which is showcased on the right here. That's automatically detected humpback whale of the coast of Hawaii. And this detection algorithm has about 6 false positives per hour and showed a reliable detection range of about 3 kilometers. So why is nobody using such a system? The system that was available so far was actually designed for noise exposure mitigation, so it had a 360 degrees field of view, and with this requirement came very high cost. It cost several hundreds of thousands of dollars and was very bulky, about 150 kilograms. Those could only be used on very large and stable vessels, and we wanted to see if we can develop something that is smaller and purpose-built just for ship strike mitigation. So here you see our new versions. Here on the left, that's the smallest one that is purpose-built for ship strike mitigation. We reduced the cost from about 500 plus K to about 10K. It is fully stabilized for roll and pitch, and the automatic detection algorithm alerts the operator within about 6 seconds. Now we have several parameters which are crucial to measure the performance of such a system, and that is the quality of the stabilization, the field of view, the detection algorithm, and then the in-time detection probability, which of course depends on the detection range, the ship of the speed, the elevation, and finally the whale behavior. Here we show the performance of the stabilization. You can see how the ship is moving on the bottom of the video here, and the horizon is seemingly stable. This is very important for the detection algorithm to work, as the detection algorithm depends on a pixel-to-pixel correspondence across images. So here's the first example for you of a whale the system detected. You can see it on the right. The whale comes to the surface and spouts. This is very close by, at about 300 meters. And I have another example here on the left of the whale. You can see the signature is much smaller, as the whale was about 830 meters away. We were lucky this year that they still got out of the water despite all this COVID situation, and we had 2 days to test our prototypes in summer 2020. We worked with humpback whales, simply because they are abundant and easy to image. And we used the National Marine Sanctuary Stellwagen Banks RV AUG. Thanks to Dave Slocum for making a lot of things possible to get us out on the water. And we were really lucky, as we imaged about 900 whale blows in 2 days. And we had a very simple protocol. We would find a group of whales that were doing something. We would approach them from several kilometers distance, and then pass them in the allowable distance, go further out, turn around, and come back and do this several times. Then we can summarize this in a detection function. So what you see here is the detection function for this experiment. On the x-axis you have the distance, and on the y-axis the number of whale blows. And basically you can understand this as where the peak is, you have the optimal detection range. After that peak you start to lose animals and you don't detect all of them anymore when they come to the surface. And there's two things to notice here. First, everything beyond 4 kilometers I would not trust. There's very few pixels at that range, so forget about it. And we have our peak at 1 kilometer. Now, in respect to the other experiments we did before, this is of course very low. You see, our experiment here was at 1 kilometer, and experiments before had those peak at 2, at 3, and seemingly even at 6 kilometers, so very, very far out. Now, what's the difference? The main difference across all those experiments is that we were at different elevations. This experiment was done at very low elevation of 5.5 meters, and the others one were respectively higher, between 16, 50, and even 800 meters elevation. So elevation is a crucial factor when you try to determine the effectiveness of such systems and how far you can detect an animal. Now, so why do I care? I care because the reliable detection distance is a key parameter in the in-time detection probability. What do I mean by that? We need to make sure to know if such a system is effective, that we can detect the whale in some area, let's say that up here in the detection zone, before it enters the exclusion zone, so the operator still has time to change the course or slow down. And to study this, we make a very simple whale model. We kind of have a ship with a virtual camera system on board. We place out some virtual whales that have a true diving patterns extracted from tagged whales, and we define 3 different depths. If the whale is below than 5 meters, above 5 meters depth, it is detectable and in danger of ship strike. If it is in between 5 and 15 meters, it's very dangerous because it is not detectable but still in danger of ship strike. And if it's deeper than 15 meters, it's not at risk. And then what we do is we just run that model several hundreds of thousands of times with different positions of whales. The whales move around, the ships move around, and ultimately we end up with such a figure. And now here I encoded the ship's speed on the x-axis and the in-time detection probability on the y-axis. And I used 2 different detection ranges, so reliable detection ranges of 1 kilometer in black and reliable detection ranges of 2 kilometers in pink. And I gave them 1 and 2 minutes. What does these minutes mean? That means that the range, the exclusion zone, is defined by I need 1 minute to change the course or slow down, or I need 2 minutes to change the course and slow down. And now we learn that if I only give you 1 minute, there's very little time to do, and I only can detect a whale in 1 kilometer distance, my best detection probability at 5 knots is about 50% of the animals. So only in 50% or even in 50% of the times you would be in time detecting the animal early enough. Now, if you go to 2 kilometers detection range, this looks already much better. You can see that we almost would detect all of them if you go 5 knots. Certainly, if you go further out and if you go faster, this number diminishes. And at the maximum travel speed of 10 knots, with detection ranges of 1 kilometer and 1 minute, we get about 90%. So I think that's the most relevant number. If we have detection ranges of 2 kilometers and we allow 2 minutes, then we end up in 0.5. So every second whale would be detected. We learn from this, if you want to go faster, your ship should be higher and your elevation should be higher so that this method can work. Now, our conclusion, as I'm out of time, low-cost real-time in-time detection of large whales from vessels is possible and feasible for ship strike mitigation. But elevation is a major factor when considering such technologies, and the speed the vessel wants to travel. So those 2 things have always be to wait. And one more notion, please regard this model that I showed you as very preliminary. I wanted to have something for today, but I'm not done with that yet. A key point as well is that fast and accurate detection is necessary. The outlook is we have long-term tests in 2021. There will be several months without an expert on board. We want to see how well do these systems actually work. Hopefully we'll be imaging North Atlantic right whales, and we try to further reduce footprint and cost so those systems can actually be deployed on a large number of vessels. And closing, I want to thank my sponsors, the ONR, OceanX, Department of Fish and Regions and Oceans in Canada, and the World Oceanographic Institution. Thank you.